Have you ever wondered why a pendulum swings back and forth, or why a spring bounces up and down? Let's dive into the world of simple harmonic, periodic, and oscillation motion. These three types of motion are integral to understanding the world around us, from the ticking of a clock to the vibrations of a guitar string. Simple harmonic motion, or SHM, is a special type of oscillatory motion where the acceleration of a particle is directly proportional to its displacement from the mean position. Periodic motion, on the other hand, repeats itself after an equal interval of time, like the uniform rotation of the Earth. Lastly, oscillation motion is the to and fro motion of a particle about a mean position, such as a swinging pendulum. Now that we have a basic understanding of what these motions are, let's delve deeper into each one. What makes simple harmonic motion, or SHM, unique? Let's explore. Simple harmonic motion is a special form of oscillatory motion, where the acceleration of a particle at any position is directly proportional to the displacement from the mean position. This means that the further the particle moves away from its equilibrium position, the greater the force that pulls it back. Now let's consider an example you might have seen before: the spring mass system. When you stretch or compress a spring attached to a mass, it oscillates back and forth in a straight line. This is a fantastic real-world example of simple harmonic motion in action. But what makes it simple harmonic? Well, there are specific conditions that need to be met. First, the motion must occur in a straight line. This is why the path of our spring mass system is a perfect example of SHM. Second, there must be a restoring force that always acts towards the equilibrium or mean position. In our spring mass system, this restoring force is provided by the spring itself. The more you stretch or compress the spring, the stronger the restoring force that pulls the mass back to its original position. Finally, this mean position must be a stable equilibrium. This means that if the particle is slightly displaced from the equilibrium position, the restoring force will always try to bring it back. Now let's jump to the angular version of SHM. In an angular simple harmonic motion, a system oscillates angularly with respect to a fixed axis. The conditions are similar, but instead of a restoring force, we have a restoring torque that's proportional to the angular displacement and directed towards the equilibrium position. So, in essence, simple harmonic motion is an oscillatory motion with a specific set of conditions. It's this unique combination of characteristics, the straight line motion, the restoring force, and the stable equilibrium, that makes simple harmonic motion an important tool in understanding phenomena like sound waves, light waves, and alternating currents. Next on our list is periodic motion, but what sets it apart from the rest? Well, let's dive right in and explore. Periodic motion is a type of motion that repeats itself after an equal interval of time. You might think of a clock ticking away with its second hand sweeping around in a perfect circle every 60 seconds. That's a classic example of periodic motion. There are a few key characteristics that define periodic motion. Firstly, there is no equilibrium position in periodic motion. This means that there isn't a central point that the motion revolves around or returns to, unlike in oscillatory or simple harmonic motion. Secondly, there is no restoring force in periodic motion. In simple harmonic motion, for instance, the restoring force is what pulls the object back to its equilibrium position. But in periodic motion, there's no force pulling the object back to a specific point. Thirdly, there's no stable equilibrium position in periodic motion. In other words, there's no point where the object would stay put if it weren't for the motion. It's always on the move. A great example of periodic motion is uniform circular motion. Think of a spinning wheel or a planet orbiting the sun. These objects follow a path that repeats over and over again in a consistent periodic way. And here's an interesting fact. While all simple harmonic motions are periodic, not all periodic motions are simple harmonic. For instance, if an object is moving in a perfect circle at a constant speed, that's periodic motion. But it's not simple harmonic because the object's speed and direction are constantly changing. Remember, the beauty of periodic motion lies in its consistency and predictability. Whether it's the ticking of a clock, the rotation of a Ferris wheel, or the orbit of a planet, These motions happen over and over again at regular intervals, like a perfectly choreographed dance in the grand ballet of physics. Thus, periodic motion is a repeated motion occurring at regular intervals. It's the rhythm that powers the universe, from the smallest atoms to the largest galaxies. Let's now swing into the world of oscillation motion. This is a motion we're all familiar with, perhaps without even realizing it. It's the back and forth, the to and fro, the sway and return. Oscillation motion is a dance around a mean position, a balance point that the motion always returns to. Picture a pendulum in your mind swinging back and forth. This is a classic example of oscillation motion. The pendulum moves from one extreme to another, always returning to the same central position. This central position, the point of balance, is known as the mean or equilibrium position. Oscillation motion is not just a random sway, it's a periodic motion, meaning it repeats itself after an equal interval of time. It's bound between two extreme points, with the object moving continuously back and forth around the mean position. But what's pushing the pendulum back to the center? What's keeping this dance going? That's the restoring force. In oscillation motion, there's always a restoring force directed towards the mean position. This force ensures that the pendulum, or any object in oscillation motion, returns to the center after swaying to either side. And here's something interesting. At the mean position, the net force on the particle is zero. That's because it's a stable equilibrium position. The object isn't being pushed one way or the other. It's at rest, balanced, until something nudges it and sets the oscillation in motion again. So let's take a look at the oscillation of a simple pendulum or a spring mass system again. These are not just random movements, they're a dance of forces, a subtle balance of motion and rest, push and pull. They're a continuous journey from one extreme to another, always returning to the center, the mean position. In summary, oscillation motion is a to and fro motion around a mean position. It's a dance of forces, a delicate balance that keeps the world in motion, from the swing of a pendulum to the vibrations of a guitar string, and so much more. Now that we've understood each motion individually, how do they compare to each other? Let's start with simple harmonic motion, or SHM. This is a special type of oscillatory motion where the displacement, velocity, and acceleration of an object vary over time in a way that can be described by sinusoidal functions. The object's path must be a straight line, and there must be a restoring force directed towards a stable equilibrium or mean position. An example of this is a spring mass system. Now, onto periodic motion. This is a motion that repeats itself after equal intervals of time. It doesn't have a specific equilibrium position or a restoring force. A common example is uniform circular motion. The motion is continuous and without a stable equilibrium position. Oscillation motion, on the other hand, is a to and fro motion of a particle about a mean position. It's a type of periodic motion bounded between two extreme points. The object keeps moving between these 2 points along any path, and there's a restoring force directed towards the equilibrium or mean position, which is a stable equilibrium position. Examples include the oscillation of a simple pendulum or spring mass system. So, what do these 3 types of motion have in common? Well, they all involve objects moving back and forth in some way. However, the differences lie in the specifics of how this motion happens. In SHM, the motion is along a straight line and there's a restoring force. In periodic motion, the motion repeats in a cycle, but there's no equilibrium position or restoring force. And in oscillation motion, there's a to and fro motion about a mean position. As we delve deeper into the world of physics, we'll find that these types of motion are fundamental to understanding a wide range of phenomena, from the swing of a pendulum to the propagation of light waves. As we can see, while these 3 motions share some common traits, they each have unique characteristics that set them apart. Let's summarize what we've learned today. We've explored the intricate world of simple harmonic motion, periodic motion, and oscillation motion. We now know that simple harmonic motion is a special case of oscillatory motion where the acceleration of the particle at any position is directly proportional to the displacement from the mean position. We learned that not all oscillatory motions are simple harmonic motions, but every simple harmonic motion is oscillatory and periodic. We also discovered that oscillatory motions are a subset of periodic motions, characterized by their to and fro movement about a mean position. We delved into the differences between these motions, understanding how each of them plays a unique role in the physical world. We also studied the conditions and types of simple harmonic motions, including linear and angular types. Understanding these motions can help us comprehend many natural phenomena around us, so keep observing, keep learning, and stay curious.